Hello, everybody. So in this video, we are going to talk about the intersection problem for one surface in the hyperbolic 3 space. First of all, I would like to thank the organizers of this section, Professor José Miguel Manzano, and also Marcos Petruccio for the kind invitation, and also Rudy Lee for the organization of this geometric analysis past, present, and future. So just to start to talk about this problem, I would like to remember the roots of this problem. So we go back to the 50th Euclid's postulate, which I just remember now. If I pick a segment of line L1 and another segment of line L2, and I intersect both these segments with another line, and if the inner angles here alpha and beta, if the sum is strictly less than pi, so the 50 Euclid's postulate says that we can continue the lines L1 and line L2 in a way that they will intersect each other. So another way to say that, which is we call the Playfair's axiom, says that if you pick a line L and a point outside this line, point P, so there is a unique line L, LP, which is parallel to L and, of course, containing P. So, this is a very old problem to understand if this 50 postulate was actually an axiom, or if we could prove this postulate using the other four postulates. And the development of the geometry starts in some way from this question: if you can prove or disprove this assertion about the axiom, about this problem concerning the 50 postulate. So trying to negate this postulate, it's better to see the equivalent form by the Playfair's axiom. So if you try to negate this, we will arrive in two possibilities. So the first one is we can have not only one line parallel to L and passing through the point P. And in this case, we discover the hyperbolic geometry. So in the hyperbolic geometry, we have a lot of geodesics, which is the line in the hyperbolic geometry, passing through a point P outside one line L, and the distance from, and these lines, L1, L2, L3, L4, are equidistant from this line L. Okay, and the other case is if you have no such line parallel to L. In this case, we have the spherical geometry. In the spherical geometry, if you just the geometry in a sphere, you can think like that, and there is no lines parallel to a geodesic, which are, in this case, the geodesics are closed geodesics, this geodesic L. So there is no other line passing through P, which is parallel to L. So in this case, they must intersect, actually. So observing this perspective from the spherical geometry in the sphere, classically, so we know all the geodesics in the sphere, so you can see that all geodesics are closed, and so also they intersect each other. So observing that, Hadamard proposed a very nice result about this intersection problem. So he considered just a surface with positive Gaussian curvature, and he proved a similar thing which happens with the sphere. So he proved that every geodesic must intersect every closed geodesic. So it's a very classical result and very beautiful result, which was the inspiration for Franco. And Franco in the 60s years, he proved a kind of extension of Habermas theorem. So he considered, instead to consider just geodesics, he generalized this for minimal surface, or in this case, actually can consider hypersurface in dimension. So he considered minimally emergent hypersurface in such a manifold complete, and he asked that these minimal surface are emerged as closed subsets. In some sense, we can think that sigma 1 and sigma 2 are properly emergent in P. And the second main assumption, is about the curvature. So he asked that the curvature, the Ricci curvature of the manifold P is strictly positive, and sigma 1 is compact. So in this case, he proved that sigma 1 must intersect sigma 2. Okay, so after this result, this kind of property was called as Franco's property, and some results were done. Here, I would like just to mention two results due to Bessa, Jorge, and Oliveira, and also due to Rosenberg in the same year. So in the first, the authors proved that if you pick sigma 1 and sigma 2, injectively emerged with bounded curvature, and the Ricci curvature is positive. So in this case, you have Franco's property, which means that the surface must intersect. Okay, so in this case, the manifold P could be non-compact because the Ricci curvature is just strictly positive. And in Rosenberg's result, he assumed the surfaces are only emergent with bounded curvature, but he assumed that the Ricci curvature is positive and bounded from below by positive constants. So in this case, the manifold P must be compact, but the condition on the manifolds, which are minimally emergent, of course, here I don't write, but I'm talking about the minimal surface in this case. And we also have the Franco's property. So here I can just pointwise that the main difference between the Franco's property to the result by Bessa, Jorge, and Oliveira and Rosenberg was that they changed the class of minimal surface, which before were closed subsets like properly emergent, and they changed for surface with bounded curvature. So they consider another class of minimal surface. Okay, so this is, I can say, the first part of this talk when I described just the results and the spherical geometry. Of course, we have other new results about Franco's property, but in a different way. So I would like just to mention here the classical ones. And the next question is, what about the intersection problem in the Euclidean space? So in the Euclidean space, actually the intersection problem is called sometimes by half-space theorem. So if you look in the literature, you can see some results calling this intersection problem by the half-space type theorems. Okay, so just to mention maybe the oldest result about this kind of intersection, but which which is very classical, and it's very easy to prove, actually. So if you consider a minimal surface in R3, which is parabolic. Here, parabolic means that the green function, the positive green function, is identically infinite. Or maybe if you like, you can think that the prime motion is recurrent. Okay, so there are a lot of equivalent conditions to define the parabolicity of a surface. So you can use N1. And if you pick any plane, two plane in R3, so you have two possibilities. Or this parabolic minimal surface intersect the plane, or they are parallel. So this result is very easy to prove because we know that the coordinate functions of the Euclidean space, when we restrict to a minimal surface, these coordinate functions are harmonic functions. And so by using Liouville theorem, because the surface here is parabolic, so you can see that the height function of this coordinate function respect to this plane is constant. So we can deduce that or M intersect the plane, or it is parallel to the plane, and since it is a minimal surface, it must be contained in the plane. If you ask also that the minimal surface is complete, so you can claim that M is also a plane parallel to the plane pi. Okay, so this result is really old. Maybe it's just a consequence of the Liouville theorem. And here I don't put any reference for that because it's really classical. Okay, we can deduce also half-space theorem, or this prove some intersection problem in the Euclidean space using a really important result, a deep result due to Xavier. So Xavier considered non-planar minimal surface with bounded curvature immersion, only immersion in the Euclidean space. And he proved that the convex hull of M must be the entire space. So what we can deduce from this result is if we pick plane, so we define half space here, which is convex subset of R3. We cannot have a minimal surface in here with bounded curvature non-planar because of this convex hull theorem due to Xavier. So we can also imagine as a consequence of this result, half-space theorem for minimal surface with bounded curvature. Okay, so some years later, Hoffman and Meeks also proved a very nice result for minimal surface which are properly immersed in the Euclidean space. So if you consider a minimal surface properly immersed in the Euclidean space, we have two possibilities: or the minimal surface intersect any plane, or the minimal surface is parallel to a plane. So here the minimal surface is assumed to be complete, and in this case, M must be a plane parallel to pi. Okay, but in the same paper, Hoffman and Meeks considered a kind of strong half-space theorem. So they consider not only one surface, minimal surface, against a plane. So they consider two minimal surfaces inside the same class. So the surfaces are properly immersed in the Euclidean space. And they proved that those surfaces must intersect unless they are parallel planes. Okay, so how Hoffman and Mix proved this strong version of the half space theorem. So they employed a very strong result due to Mix, Simon, and Yao, which we can think like a separating result for minimal surface properly immersed in the Euclidean space. So this result says that if you pick two minimal surface properly immersed in the Euclidean space, we have only three possibilities for the position of this surface. So the first possibility is this surface must intersect in a proper way, which means that the intersection must be a subset, not like a point. So we have a big measure of this intersection subset. Also because we know that minimal surface cannot intersect on in a touching way because of the maximum principle. Okay, the second position for them is they are parallel planes. Of course, the planes are minimal surface, so this situation can also happen. Okay, and the third possibility is we have a minimal surface here and another minimal surface here, and there is a plane in between them. But if we apply the half space result against the plane, so we deduce that this third possibility cannot happen. So they deduce the strong version of the half space theorem just applying this separating result. And moreover, so Bessa, Jorge, Oliveira, and also Rosenberg, they consider in the same paper, they consider this kind of strong version of the half space theorem. So as before, they consider the strong version inside the class of minimal surface immersed in the Euclidean space, but with bounded curvature in this case. So they proved the same result independently, and also the proof are different in some aspects. And they prove that the surface must intersect or they are parallel planes. So as before, the main part to prove this kind of result is to build a plane in between them. So in such a way, they also use the same idea of Hoffman mix. But to build this plane in between the surface, they applied all the geometric way to prove that. Okay, so in the same paper, Bessa, Jorge, and Oliveira also propose a kind of mixed half space result in a strong way. So now they consider not only surface with bounded curvature, but they consider also one surface with bounded curvature and the other surface is properly immersed in the Euclidean space. So if you pick M1 as a minimal surface, which is proper, and M2 with bounded curvature. Here, all the surfaces are complete. So they have this strong version of the half space theorem. So the surface must intersect or they are parallel planes. But in the same spirit, Bessa, Jorge, and myself, we consider this kind of mixed half space theorem, but now we go back to the first result that I showed you regarding parabolic minimal surface. So now we will compare the class of parabolic minimal surface. Now we don't need to assume that this surface is complete. So in this case, particularly, and M2, the other minimal surface, we assume with bounded curvature. So in this case, we can prove that the surface must intersect or they are parallel but not planned, because I'm not assuming that M1 is complete. But if you assume M1 is complete, so in this case, both surfaces are planned in parallel. We will not show here how to prove that, but I can say that the idea is not to build another surface in between this surface, so it's a different idea. Okay, so but now, what about the hyperbolic geometry? So, which is the main subject of this video. So, the first point is now we need to analyze which are the corresponding surface that you can treat in the hyperbolic space. So, first of all, we know that one surface, what is one surface here? One surface is a CMC surface, a surface with constant mean curvature, equals to 1. So I will just write one surface, meaning that the surface has constant mean curvature equal to 1. And all the surface here will be immersed in the hyperbolic space. So first of all, just recall that there is a very nice correspondence between minimal surface in the Euclidean space and one surface in the hyperbolic space. So the first coincidence is we have for minimal surface in the Euclidean space the Weierstrass representation, and for one surface in the hyperbolic space we have the Bryant representation. So they share this kind of representation, which is really important in the theory of minimal surface and also one surface in the hyperbolic space. And another aspect is the Lawson's correspondence. So we can build using, we can see from a minimal surface in R3 a cousin surface, we can say, in the hyperbolic space, which has constant mean curvature equal to 1. So there is a correspondence between a minimal surface in R3 and this one surface in H3. So it is very natural to consider the same problem, the intersection problem, in for surface immersed in the hyperbolic space, but now not minimally immersed. So now the best choice is to study the geometry of this problem for one surface. And Rodriguez and Rosenberg, they consider the intersection problem in the hyperbolic space, and they proved a really nice result. So first, we just think about M, the surface, properly embedded in the hyperbolic space. And we assume M has constant mean curvature equal to 1. So the first result that I just summarized here in the picture is, if we consider a holosphere, which is also and one surface, so we cannot have n lying in the mean convex component defined by the holosphere. So here is like this inner part of the holosphere. So M cannot be inside the holosphere unless it is a holosphere. And moreover, if you consider M here like outside this holosphere, but the mean vector field of M points to the holosphere, so M must be also a holosphere. So the case here is M cannot be in the mean convex region defined by the holosphere, and also the holosphere cannot be in the mean convex connected component defined by the surface M. So this mean convex component is really important here in this case of surface with constant mean curvature. And the second result is where they consider the catenoid cousin, which is the cousin of the minimal catenoid, but now in the hyperbolic space. So we have the same kind of result, but here the result is more restrictive, because in this case, we cannot have M inside of the mean convex region defined by the catenoid cousin. And we also cannot have M in such a way that the catenoid cousin is inside the mean convex, the mean convex component defined by M. So in this case, we don't have this picture here. And moreover, if we consider like a strong version, so we just pick one surface properly embedded in the hyperbolic space, and we assume that this surface define a mean convex region, like in this picture. So this cannot happen. So again, if you have two minimal surfaces properly embedded, not minimal surface, one surface embedded in the hyperbolic space, so they cannot define a mean convex region between them. Okay, so this is just to point wise that this mean convex side of the surface is really an essential point to consider the intersection problem. And I would like also to point wise here to mention, this is a particular result due to Mazet, because the result due to Mazet is more strong, but I just rewrite here the result for the hyperbolic space specifically. So this is just a particular case of his result. And so Mazet considered one surface M1 in the hyperbolic space properly embedded and parabolic, and also with bound curvature. And M2 here is just a one surface properly immersion. So M2 is not embedded. So we can describe here two possibilities. So the mean convex side, so we have this M1 surface here defining the mean convex side, and we put here M2 inside this mean convex region. So in this case, Mazet proved that M1 must be equidistant to M2. So here, this symbol here, parallel, maybe has no meaning, but I would like just to say they are equidistant surface. Okay, so in this case, it's very easy. M2 must be equidistant to M1. And in the non-mean convex side, what means that here I define the mean convex side above of M1, but M2 is not the mean convex side of M1. But in this case, M2 defines a mean convex region, which is this one, and M1 lies inside this mean convex region. So in this case, also, you can say that M1 and M2 are equidistant. So we can see here how we need this assumption about the mean convex side. And furthermore, we can deduce from Mazet results, these results, mainly the first two results for the catenoid and the horosphere, because they are one surface embedded, proper, and also parabolic with bounded curvature. So this M1 here can be both the horosphere or the catenoid. And M2 now is just properly immersed, not embedded. So Mazet is a kind of generalization of the first two cases of Rodriguez and Rosenberg results. Okay, so inspired in these results, Bessa, Cruz, and myself, we propose this theorem. So we consider M1 just one surface properly immersed, not embedded. But now we have a technical assumption, maybe just technical, maybe we can drop this assumption in the future, but now we need that. So we assume that M1 is not a whole sphere. And M2 here is another one surface, but with bounded curvature. So we do not assume M2 is properly immersed or embedded, just bounded curvature. So in this case, M2 cannot lie in the mean convex component of the hyperbolic space minus M1. So when M1 is properly immersed one surface, so it will split the hyperbolic space in maybe several connected components. And what we can say is M2 cannot lie inside any mean convex component of the complement of M1 in the hyperbolic space. And as a very nice corollary, we have that if we take just M, a one surface with bounded curvature, so M cannot lie in the mean convex side of a catenoid cousin. So this corollary is a kind of correspondent result of the catenoid cousin proved by Rodriguez and Rosenberg. So there they consider a one surface properly embedded, or maybe by Mazet we can just consider a one surface properly immersed. And here we can prove just a little result, but we can replace the surface inside the catenoid cousin. Instead to be proper, we just consider that the surface has bounded curvature. Okay, it's a really good corollary, which I enjoyed a lot. And let's see just a little proof idea of the theorem. So how to prove that? First of all, I will consider M2 inside some mean convex connected component of the complement of M1. So the proof will be by contradiction. We assume M2 here in blue is in a mean convex component of the complement of M1. And I will denote this by omega. So omega is this mean convex component. Okay, now we have two cases. The first case is M1 intersect. So M1 intersects the closure of M2. But of course, we are assuming by contradiction, so M1 does not intersect M2. Okay, so in this case, we know that M2 has bounded curvature, so we will use in a strong way this assumption. So first thing here, we pick a point P in this intersection because we are assuming that it's not empty. And the first claim that we can do is there is a complete one leaf passing through P and inside the limit set of M2. So we know that we can assume that M2 is not proper. And in this case, it has a limit set. And it is very easy, not too much easy, but it's reasonable to prove that there is a one leaf. Here, one leaf is, I mean, there's a one surface passing through P and inside the limit set. So how to prove that? We use that M2 has bounded curvature, and also the ambient space has bounded geometry. So we can pick a sequence of disks, which I just draw here, which these have radius that cannot, I mean, the radius of these disks are bounded from below uniformly, so they do not decrease when I convert to the point P. So since these radius are bound from below, so I have another disk here in the limit. So I can plug in the limit set a disk, which is a one surface locally, and since the boundary of this disk are also in the limit set, so I can also put another disk, and I can build this one surface in a complete way. But moreover, we know that since M2 is inside the mean convex component of the, which we call omega, and these disks are converging to the point in the limit set which lies inside M1 by assumption. So by the maximum principle, we can say that this limit leaf S lies inside M1. It's just a little simple application of the maximum principle. And moreover, we can prove that the leaf S is strongly stable. So just to remember, a strongly stable surface is a surface which satisfies this inequality, this integral inequality here, or we can just think about the existence of a positive non-constant solution for the Jacobi equation, which I described here. So just saying strongly stable in this way. But now, so we build this one leaf, which is a complete one surface, strongly stable. So we can say that S is also totally umbilical by a very beautiful result due to mixed pairs and Ross. And in this case, we deduce that S is actually a horosphere, but because of the maximum principle, S is inside the M1, which is a proper one surface. And we have a horosphere inside. So in this case, M1 must be a horosphere, but we are assuming that M is not a horosphere. So we get a contradiction in this case. Now, let's see the second case. In the second case, M1 does not intersect the closure of M2. So we have some space in between the closure of M2, which I just draw here in blue, and the boundary of omega, which is inside M1. Okay, so we have this picture here, we have some space in between them, and the idea now is I would like to build some surface in between them, which will be again a horosphere, and we will get a contradiction. Okay, how to do that? So first of all, we take a big ball, BR, which intersect the closure of M2 and also M1. Okay, so this big ball we can pick, and now we just draw here the tubular neighborhood of the closure of M2. Actually, just draw here one part of the tubular neighborhood, of course. And okay, so since M1 does not intersect the closure of M2, so we can assume that this tubular neighborhood for some R really small does not intersect also M1. Okay, so in this case, I will consider DR the region which I can say is omega minus the tubular neighborhood, and we make the intersection with the ball. So the region DR is just this region here, the put, you can see. Okay, and we assume that the boundary of omega inside the ball is inside the boundary of DR. So these are the assumptions to build this set DR. So it is a connected set inside the ball, and the boundary of the set DR contain also the boundary of omega inside the ball. Okay, so now we consider a family of subsets of DR which are open. Sorry, I'm touching here, and yeah, you know. So Q here are open subsets, and the boundary are rectifiable. And we assume also the boundary of the tubular neighborhood, now just the half part, is contained in the boundary of K. Okay, so what is the picture? K is like this subset here that I describe here. So K can be a subset which maybe touch here the boundary of the tubular neighborhood. Now that the neighborhood is just R over 2. And okay, we assume some regularity of the boundary. And okay, so what is the idea? The idea is I would like to define a functional, which I will call F, acting over this family F, this calligraph F, and the functional is, of course, well known. So the functional is defined on the subset Q. F of Q is the area of the boundary of Q minus 2 times the volume of the subset Q. Okay, so my idea now is to minimize this functional. And how to do that? Oh, okay. Before, to minimize, actually, we just apply a very strong result to find minimum for this functional. But before, we just analyze some possibilities. Okay. First of all, I will split in 2 cases. So the first case is assume that Q intersects some tubular neighborhood of the boundary of omega. So I just put here this line here in white. So this is it is a kind of tubular neighborhood of the boundary of omega. And if you assume that Q intersect this tubular neighborhood, so we can find another element of the family F which does not intersect this tubular neighborhood, some a bit small neighborhood, and the functional applied on this Q prime is less than the functional applied in the previous subset Q. So you can modify our subset. So in this case here, we can just modify our subset like this, and we can erase this part. So this first condition here is just to say that the boundary of our subset Q, we can think like far away from the boundary of omega. So in the end, we will need to do some argument, some convergent argument. We need to put do some convergence, and so I would like to have a good distance from the boundary of Q and the boundary of omega. Okay, the second observation here is if the tubular neighborhood here below of the surface M2 intersect. That you pick the intersection of this tubular neighborhood with the subset dr. So I'm just talking about this subset here. And if you assume that, actually here is R over 2, I'm talking about this one, this big one, okay? But in this case, if this intersection is not completely inside the subset Q, so in this case, I can find another tubular neighborhood and another subset in the class such that the tubular neighborhood, of course, here is intersected with the subset dr, I'm sorry. Now it is contained in this new subset Q prime, and again, the functional decrease. I mean, the functional is less than the original one, the first subset. So in this case, I have drawn here. In this case, it's like here we have the subset Q, and if it happened, so I can just increase my subset, and now I'm sorry. So yeah, okay, my subset is like this. I have also the ball here. Sorry. And now I can just increase my subset, and Q now is new subset Q prime will contain this tubular neighborhood. Okay. Again, for what we need that? Before, in the first observation, I just observed that the boundary inside of dr is far away from the boundary of omega. And now this is just, again, to say that the boundary of the subset Q is also far away from the tubular neighborhood. I mean, it's far away from some tubular neighborhood of the closure of M2. I'm sorry about this. The picture is now. Okay, so the idea now is I can apply a very strong result for compactness result for integral currents to prove the existence of a minimizing inside this family. And of course, this minimize will satisfy this both conditions here, 1 and 2. Okay. And in this case, this Q infinite, the minimizer of the functional, it has a boundary inside the interior of dr. Just recall here is the subset dr. And we have here, which I call just SR, is the boundary of Q infinite inside the interior of dr. And why I'm very interested about that? The main point is, by regularity theory, SR is a smooth one surface strongly stable. This is because SR is a solution, a local solution for there is a parametric problem. So the regularity theory says that SR is a smooth one surface and strongly stable. Okay. So now I just do a limit process to obtain a strongly stable one surface, which will be also complete. And in this case, because of the observations that I put here, we can deduce that after this limit process, we obtain S infinite surface which do not intersect the closure of M2 and also does not intersect M1. And again, since it is and one surface strongly stable and complete, so it is totally umbilical, and again it is a horosphere. But by Mazet results, we know that M1 must be a horosphere, because this horosphere would be in the mean convex region of M1, and since M1 is proper, so Mazet's result says that M1 must be a horosphere, but it is a contradiction again. So this is just a little idea of the proof. Of course, maybe for some details, you can read the paper, which is available on archive. Now, what about Frankel's property in this context of hyperbolic geometry? So just to remember, for minimal surface, we considered before the Frankel's property for minimal surface immersed in a manifold with rich curvature positive, so it's strictly positive rich curvature. Now we will consider one surface, and the corresponding curvature is the rich curvature is strictly larger than -2. Okay, here my rich curvature is not normalized. Okay, so in the same paper, Bessa, Cruz, and myself, we consider also the Frankel's property in this setup here. So we just pick P as a manifold, a complete manifold with rich curvature bigger than -2, and we assume M1 is a compact one surface, and M2 is one surface with bounded curvature. So it's not proper, it's not embedded, it's just one surface with bounded curvature. In this case, we proved that M2 cannot be inside of a mean convex component of P minus M1. So just to show how sharp is this assumption here on the rich curvature, we put here an example. So we consider the hyperbolic cusp. So the hyperbolic cusp here is just a product manifold P3, which is the line times the torus, and we consider this metric where G is just the flat metric. Okay, so it's very easy to compute the rich curvature of this manifold is -2, and also we have that the slice of P3 are one surface, and of course you can see that this first one surface here is in the mean convex side of this surface below. So the theorem is not true in this case. Okay, so if we put the rich curvature equals to -2, so we cannot have this kind of result. Just a little idea, very fast idea for the proof of the result. Again, we consider two cases. The first case, M1 intersects the closure of M2. And in this case, again, we just consider a point P in the intersection, and we can prove the existence of one surface SP containing P, which is strongly stable. But in this case, it contradicts this very famous result by Nix, Perez, and Ross, which is, so Nix, Perez, and Ross proved that there are no complete strongly stable one surface merged in a complete manifold with rich curvature bigger than -2. Actually, this result, I just put here the curvature equals to -2, but it's can be for any constant. We just normalize here. Okay, so in this first case, we get a contradiction because we don't have such strongly stable one surface inside a manifold with ridge curvature bigger than -2. So the first case cannot happen. In the second case, M1 does not intersect the closure of M2. And since M1 is compact, there are P in the closure of M2 and Q inside M1 such that they realize the distance between the closure of M2 and M1. So, and in this case, since the intersection is not is empty, so the distance is positive. Okay. So we consider again SP as a limit one leaf contained in the closure of M2. So we build this complete one surface inside the closure of M2. And in this case, there is a minimizing geodesic sigma and P such that sigma starts on Q. So sigma is this segment in red here. So it starts on Q and finish on P. And we can consider a foliation by parallel surface to M1. So we would denote by VT, for T in between 0 and L. So the foliation here, I just put in blue, VT. And the main point here is, since the distance is attained, so this foliation can go from M1 up to touch SP. Okay, so this is the main point that we consider here. Okay, but now we know that how the mean curvature evolves along this parallel surface. So they must satisfy this equation here, 2 times first derivative of the mean curvature function is equal to the ridge curvature plus the square norm of the second fundamental form. And by assumption, it is bigger than -2. And here we also use the Newton's inequality plus 2 times 8 the mean curvature of the parallel surface. And because it satisfies a Riccati equation, so we know also that it is strictly positive because 8t must be bigger than 1 or equal to 1. So in this case, we conclude that the mean curvature of the parallel surface VL must be bigger than 1, which is a contradiction because we are touching VL touch the surface SP in the mean convex side of SP, so we cannot have this kind of sorry, it's in the other side. Just look at the picture. So VT arrive here in VL, and SP is inside the mean convex side of VL. So by the maximum principle, the mean curvature of VL must be at most 1. Okay, so it contradicts the maximum principle, and again, we cannot have this situation. So this finished the proof, and so that's all. And I would like to thank your attention. And